most of this work is available, as I said, on YouTube and Wikipedia. Basically, are the principal sources for most of this stuff. There's a few other things that I'll mention in there. So the outline is basically there are three themes: batteries and how they work, the grid and the importance of storage, and a great word which I got from Sabina Hostenfelder, the Dunkelflaute problem, which is what happens when there's basically darkness and no wind. And then the batteries on the grid. We'll talk a little bit about the new battery technologies if we have time. Some of this may end up having to be a second talk later because I think we may run out of time. And something about the business of batteries. There are two local companies that are very much involved in developing new batteries, and there's a company that's developed technology for recycling old batteries. And then news, if we have time, of batteries on the grid, and some links. So the basic three themes are batteries and how they work, a little bit about the history of the batteries, a little bit about the physical chemistry of the batteries, and lemons and pressure-treated lumber. This thing was a very popular discussion topic a few years ago. It is not a battery as far as anybody can tell. It was discovered in what is now Iraq. In the original discovery was in the early 20th century. And then it was rediscovered, and then it was lost again. And the picture you see is of something that was in the Iraqi museum. It was stolen from the museum when the Second Iraqi War began. What it consists of, though, is what you could make a battery, and indeed the Mythbusters basically took this and studied the myth in the fashion of actually making a battery out of it. It turns out it probably more than likely was misinterpreted in terms of the age. People thought it might be from 200 odd BC, but it more likely somewhere in the around 400 AD time frame, because of the misinterpretation of the type of pottery. It's not Parthian. It's almost definitely Sasanian, which is a pottery style associated with the empire that existed in that period, in the time just before the beginning of the Muslim conquest of that part of the world. So it's apparently just a container for scrolls. Scrolls were placed inside these copper tubes and placed into a ceramic pot and sealed up. And they had in the center of the scroll an iron rod, which the scroll was wound over. But if you put acid in here, you could make a battery out of it. This also, while it was a battery, is not the kind of battery we think of today. This actually might be the definition of an ultracapacitor. In 1745, Pieter van Mussenbroek of the Netherlands, in Leiden in particular, invented a bottle to store electric charge. People were already playing with electric charge from time back to the Greeks, but in the late 18th century, they started really seriously getting involved with interesting things with electric charge as ways of collecting large amounts of charge were being developed. And the way to store it was to basically put the charge on an electrode that was separated by air from another electrode. The air formed a dielectric. It was a capacitor, and Benjamin Franklin had this array of these things built, and he called it a battery after the artillery battery idea, that there was a concentration of Leyden jars in one place. And as we pointed out, there's 100 years before the electric motorcycle was first proposed, which used a battery not of this type. This is an image from the Franklin Institute. So let's go back to see how batteries really started, in a sense. There was an Italian physician, physicist, natural philosopher, whatever you want to call him, Luigi Galvani. He was working in Bologna, and he was very interested with these kinds of things. This is a contemporary from that period, but nobody's really sure who did the engraving that produced this plate. This is a machine for generating static electricity. You turn this crank, and there's a little ball here, and this little contact scrapes on the ball, and you generate a charge. It's a kind of a primitive version of a Wimshurst machine, which in turn is sort of the sort of predecessor of the Van de Graaff generator. But in addition to this, of course, Franklin had been playing with natural electricity in the form not just of electricity you could generate by rubbing things yourself, but nature rubbed things and generated huge voltages, huge currents, huge amounts of charge in the form of lightning. Franklin was absolutely inspired to study lightning, produced the lightning rod, gave us a lot of the terminology we use today. In addition to battery, Franklin is responsible for deciding that charge of the electrons was negative. He basically then essentially distinguished between charge and current, though he didn't really understand current. And he sort of provided a lot of the underpinnings for things. As I said, Galvani took some of these ideas and proceeded to do strange experiments on frogs, which he had been also involved in dissecting. And one of the strange experiments involved hanging the frog's legs, and basically the frog's legs were attached to a brass structural piece, and then he used a scalpel, which was an iron piece, steel, and touched the frog's legs when he was making apparently originally a demonstration in front of a class on dissection. The frog's legs jumped. He could have jumped too, probably. And then he went back to the lab and started playing with frogs and electricity, thinking that, well, there's some sort of animal electricity. Well, it turns out there is, but that was not the source of why the frog's legs jumped when they were disconnected from the rest of the frog. He published this work just shortly before his death. He died in, I believe it was 1792. This, as you can see, was published in 1791. Of course, everything was published in those days in Latin, but basically you can read it. It's talking about muscular and electricity. His sort of alter ego nemesis, if you want, and maybe not quite right, counterpart, Alessandro Volta, basically said, no, it's not the frogs that are responsible for the electricity, it's the metals. And he decided to do a replacement for a frog. Frogs are mostly salt water, so he made a series of discs of metal and paper soaked in salt water, and the charge that he observed, the voltage that he observed ultimately, he didn't, of course, have a measure of voltage, but the name Volta gave way to voltage, gave us the name voltage. And the basis of this thing, though, he misinterpreted it in some sense. He thought the reaction was a reaction between the copper and the zinc. He saw the copper didn't seem to be affected too much, the zinc more so. He didn't realize that while there is a redox reaction going on, oxidation occurs at the zinc. Zinc definitely does corrode, but the copper serves really as only an electrode for the process occurring of what happens at the cathode reduction, which is hydrogen ions become hydrogen gas. In the meantime, you get electrons that you can run around in the circuit. Napoleon, of course, had conquered Italy, and so he was the emperor of Italy, and Volta was already quite famous. And this is a painting from the period when the event occurred of Volta demonstrating the electric pile, as it was called, because it was a stack of stuff, to Napoleon. And this made everybody suddenly realize that in addition to static electricity, there was another kind of electricity. People kept on using these things, even though they were difficult to use because the dealing with the hydrogen. And in the period of about the early 1830s, while batteries were being used to do the basis of electrolysis and discovering how to separate metals from their salts and things like that by Humphrey Davy and Michael Faraday, John Frederick Daniel was looking for a way to get rid of the hydrogen problem, and he came up with the idea of a second electrolyte that would consume the hydrogen produced in the first. And later, this was improved upon by a Frenchman by the name of Carod. And this kind of a cell, the so-called primary battery, was in use in telephone offices in the United States as late as 1950s, 52, 53 maybe. This is from the Smithsonian Natural History Museum. It's a recreation of what Daniel had done, and this is his original drawings, and this is how it works. It's sort of back to the frog in a sense. So you have the zinc, and you have the copper, and then you have the connection, which is the frog. Sulfate ions and zinc ions can flow through this salt bridge. And in this cell here, there's, in addition to the copper, there's copper sulfate. And over here, there's zinc sulfate. This is done with just sulfuric acid. And when you stick the electrodes in there, you get these reactions. But this demonstrated that the reaction that was really important was what happened here on the zinc electrode. The copper, again, basically providing the means to handle the redox part of the reaction. In the next improvement, basically, is the invention of, those are all batteries that only went one way. When the zinc was consumed, that was it. In 1850s, basically, Gaston Plante in France moved around a bit, so that's just as France. He basically realized more about the fundamental electrochemistry. I have a book actually written not by him, by one of his colleagues, and it's called the Traité d'électrochimie, and it was published in France in 1863 or 64. So it's very much contemporary with this time frame. Electrochemistry was becoming a very hot topic. Well, he came up with this idea. You could use lead and an acid and make both the cathode reaction and the anode reaction operate with lead. The difference being one was lead in an oxidation state to start with, and then it would be reduced to lead metal. This was the state of full charge. This is what happens when it discharges, but you can put it back in this form, assuming you don't run into problems that occur with crystals of lead sulfate forming and blocking some of the reaction products from getting out and things like that. But this is the basic idea of the lead acid battery that still exists today in most cars in the world. Got rid of some of the problems with the work of Faraday, who basically figured out a way to take a lead grid lattice and then press lead oxide paste into it. Made it easy to manufacture. So the question then comes back to, why are these things of interest? Well, because of the breakthrough pioneered by Nikola Tesla in the 1890s, not that far back, not that far after Faraday's work. And that's where Michael Faraday's basic idea of generating electricity is put into a more practical form with what is known today as polyphase AC, which means that you have, depending on the configuration, for 3 phases, you would have 3 or 4 conductors, and you would maintain amongst these conductors relationships, and as well as along the transmission lines. Now, Tesla did this in the 1890s. Maxwell's work was coming along and understanding electromagnetic theory, and there was an amazing expansion of this idea, and with the modern world is made really based on those fundamental principles. That you have a constant universal AC frequency, you have a constant universal phase relationship amongst the different phases, you have a constant universal voltage, AC voltage, so it's you're measuring it changing with time, but it's staying constant over a long period of time. And you have a minimization of reactive power. And this one is very important, because anytime from the work of Ampere, the work of Faraday, and then codified together in Maxwell's equations, anytime that you have a inductor in the circuit or a capacitor in the circuit, there's a phase difference between the voltage and the current on or across that element. The problem comes from not capacitors in the circuit, because there aren't that many places where you have naturally occurring capacitors in a circuit, but inductors. Anytime you have a motor, you have an inductor. And so if you have big industrial facilities, you might have the voltage and current shifted from being in phase to being out of phase by a considerable amount. And this causes currents to have to flow back and forth on the wires that are not doing any work, but they're burning up the wires or heating the wires up, dissipating real energy in the process of meeting the criteria for the reactive elements. So you can balance this by having counter-reactive elements. You can have capacitors that are in the grid that compensate for the reactive energy that's being wasted. But ultimately, the best way to handle these things is to have, as loads change, to have loads that can react. That goes back to Newton, right? And the best of these things has been spinning big chunks of steel with some copper wound on them. Generators, basically. So the main task of the manager of the electric grid is to keep the current flowing without there being a lot of reactive power and keeping these phase relationships and frequency relationships constant. So basically, Tesla gave us the overall grid architecture. I had a slide with the image of it, but it's gone. I don't know where it went. I'll put it in when I put this into the material for the talk. And basically the idea is you have a generator, you increase the voltage to the transmission voltage with a transformer, you transmit the signal, you transmit the AC to the area where you want to consume it, and then you step it down to the voltage that's usable and safe. And that's what you see on the street in front of you if you have overhead power line. You see a high voltage, relatively high voltage, 1,000 volts comes along, transformer, a couple hundred volts that you can handle easily in your household appliances. Of course, to interconnect these things, once you have multiple sites, you need to make sure that you keep all these rules working over large scale. And this has been a challenge with renewables because of the fact that the renewables are not always there, and they come and go in an intermittent way that's really erratic. In some cases, the solar energy is, if you're in a place like Nevada or something like that where it's relatively clear most of the time, you can sort of anticipate the variation in the energy from the sun. But wind energy is highly erratic. So this gives rise to the problem that the sources not only are erratic, but they're even poorly matched to demand because, for instance, the peak demand in the wintertime can often occur when there's very little sunlight available, obviously, and may not even be necessarily significant wind available. And that's what is known, thanks to the German language, which has in the 19th century, the French fought it, but the German language was really the international language of science and technology. And they gave us this great word, Dunkelflaute. And when you include the cold, you get the real serious version of the problem. And Sabina Ossenfelder will talk about this in one of the videos. So this basically is the challenge that we face. And the method that we use to overcome this problem is energy storage. And there are many different forms of energy storage, really focused on batteries, but indeed today the dominant form of energy storage in the entire planet is hydroelectric energy storage. Both hydroelectric energy storage, where you control a natural source and you open the valve when you need the electricity, and pumped hydro, where you actually can make it into a rechargeable battery, where you pump the water up to a higher level and then run it back down when you need the energy. One of the most successful examples of this was built by a company that is now part of Eversource. The company at the time was called Northeast Utilities, and they had built a number of nuclear power plants along the Connecticut shoreline and had this huge surplus of electricity they didn't know what to do with in the middle of the night. The demand would be very low, and the nuclear plants don't like to be throttled up and down, basically. So what do you do with it? Well, you take a reservoir that's artificially constructed near the Connecticut River, and you create a altitude difference between an upper reservoir and a lower reservoir. And in the daytime, you use the electric energy from the nighttime, you use the electric energy from the nuclear plant to turn what are generators backwards as motors to pump the water up to the upper reservoir, Northfield Mountain. You can go visit it if you want to. There's a nice little park up there. And then daytime, you open the valve and let the water go the other way. You can compress air and store air underground. You can have spinning metal. You can have mechanical separation in altitude with other things other than water. People have built several of these things, but the scale of them, as you'll see in one of the talks, Sabine's talk, is that nowhere near the requirement. And you can use batteries, and of course, we're producing huge numbers of lithium-based batteries these days for both various consumer products, cell phones, computer, laptops, cameras, etc., and also in cars. Producing large numbers now of batteries. Tesla produces, under license from Panasonic, basically huge numbers of batteries for their cars. But it's still a very small fraction of the number needed to actually meet the requirements of a grid which would depend on the renewables as the dominant sources. So without much more than that and the introduction, we can start the first of the videos, how batteries work. This is part of an electrical engineering series that's available on YouTube, and it's pretty well done.
Just a quick question, Ted. When
Sure.
was the concept of electricity as we know it now first identified?
Well, the words are Greek, and there were a number of Greek philosophers who played with static electricity in circa time of Alexander, essentially Alexandria, and a little after the founding of Alexandria, so about 300 BC. There were perhaps people playing with static electricity before that, but that's where the major significant work was done. People like Democritus, who hypothesized the atom, Archimedes, Eratosthenes, Samos. There were many of these Greek philosophers who we would today call natural scientists or physicists or whatever, who studied these things using the tools that were available. Of course, they had very limited instrumentation. They principally used their eyes. And the one miss was electromagnetics, which became very close. People were playing with magnets, and they were making toys that were magnetized move by having a person sitting underneath the table moving a piece of lodestone around. And the iron in the toys basically followed the lodestone. And you can just imagine that we were very close. If you had simply made a circuit out of these pieces of iron, you would have had currents flowing in those pieces of iron. You would have anticipated Faraday by thousands of years. And who knows where we would have been at that point. And at the same time, Hieron of Alexandria had been working with steam turbines. They were very crude, but he had the basis to be able to power toys that were actuated by magnets. So, okay, does anybody have any questions? It was pretty basic, but it covered a lot of the key elements that will get discussed at much greater scale in the next couple of these things. Okay, so that's one perspective on how these things may fit in the long term. The scale, however, you will see in the next talk from Professor Hosenfelder, is not the kind of scale that's really needed. We're talking petajoules of storage, not mega or even giga. I'm sorry, what was the question again? I didn't hear the end of the question.
Yeah,
Good, sorry.
okay. So, they're giving this unit of, $400 or $500 per kilowatt hour, for the storage.
Yeah,
But I thought I paid about 20 cents a kilowatt hour for electrical power. And
yeah,
I don't
but
understand the units.
that's because you're paying for very little storage. Uh, Whether you generate it or whether you store it, you have a capital cost that you have to accommodate. And when you run something continuously, like you may pay a lot of money for a nuclear plant, but when you run it continuously over a long period of time, that gets amortized. The problem with these storage things, and of course the estimates are very hard to really pin down still, with the exception of pumped hydro, because we do have a lot of experience with that. You don't really have a good sense of the total impact on delivered energy. So, for instance, Northeast Utilities with the North Field Mountain system embedded in their system, which was of course part of the ISO New England system, that didn't quite exist at the time, but when it started, they were buying electricity and selling electricity from different sources, and the amount of energy that came in and out of the Northfield Mountain thing varied depending on demand and stuff like that. And so all of these things have costs. And when you add all those costs together, including operation maintenance costs and amortizing the transmission lines over time and things like this, then you get the number that you end up with, which is in turn somewhat of a contrived number in the sense that uh, when I was on the Austin Electric Utility Commission, we had major parts of the city of Austin that didn't pay real estate taxes. So the city was using the electric utility to tax the University of Texas and the state capitol complex and the Air Force, who didn't pay real estate taxes. But they realized that if they raised the rates too much, they would end up putting on their own generating plant and taking the city out of the equation completely. So it was a careful balance of how much you put on the taxpayers who couldn't make their own generating plants and how much you put on those non-taxpayers who could. So all these numbers are adjustable in various ways. That's why we have public utilities commissions and things playing with the numbers and stuff. And they have consultants that they hire that work out the numbers and transfer them. Now with the more deregulated energy systems, a lot of it is determined by spot market prices and stuff. If you go on the ISO New England website, you can see a color that will show up immediately when you first go on the website, and that color is telling you what the cost at that instant is for electricity. So if you're in a period of relative low demand, all of New England will be green. And if you're in a really rotten period when you have a lot of demand, it might be yellow, orange, or even red. And that means the difference in price per megawatt hour, because they deal with much bigger chunks of energy and time, varies between about $12, $10, $15 per megawatt hour at the green state, which is the best. Typically, you're around 25 to 30, which will translate roughly into the price you would see over a long period of time in around 20 cents or so. But it can be as high as $200 or $300 a megawatt hour when things are bad. And if that was to persist, your energy bills will go through the roof. Yeah, there you go. Currently green. Currently, can't read it. Somebody read it, $50, something like that. Yeah. Yeah, $50. Yeah. So you can see right there a lot of the things we were talking about. That system load graph, if you roll back to the system load graph on the left-hand side, that shows you the projected demand, the current demand, and yesterday for comparison purposes. And you're seeing that right now we're exceeding the projected, the blue is the projected, and we're exceeding the projected demand by a little bit. And it may be a little bit up or down, and that will affect the price. And that's what that other graph over there on the side is. That's the hourly price at certain hubs that you see on the green thing, and it averaged out over the whole thing. And you can see that at different periods of time there are expected different prices, and then there end up being a closing price that turns out to be maybe a little bit above or below whatever the expected price was subsequent to the completion of that day's operations. There's a whole bunch more to it, but the system is based on bids for long-term commitments combined with spot market prices that are need to fill the gaps when things happen.
So that's like 5 cents a kilowatt hour. That's a wholesale rate, and we're paying several times that for retail.
Well, yeah, because this does not include the distribution costs. The ISO New England is the transmission and generation part of the equation. Once the energy gets into the hands of the person who puts it into your socket, then there's additional costs.
And we have like 6 sections on an electricity bill these days, which are generation, transmission, distribution, recyclables, and other things, right? So they add on top of that.
That's right. Yeah, and you pay also for the people sitting in the building over there on the if you're operating with Eversource like I am, the people sitting in a fancy office building, the Prudential Center, who basically are shuffling the papers and whatever. Or nowadays it's mostly done through a website that you hook up to, but they still have to be paid their salary, their benefits, and all that kind of stuff. So it all adds up in the end. This is only the raw materials to construct the energy costs, basically.
Can I ask a further question?
One thing now we're on this page. If you scroll to the right now and down, you'll see the distribution of where this energy is coming from. If you go down, over a little to the left now.
Resource mix.
Yeah, that's it. Yeah,
Round that one.
Okay, so this is the current mix as of this instant. 53% of the energy is generated by burning natural gas. 19% comes from a number of nuclear plants. 18% is coming from net imports. 6% comes from hydro, 4% renewables. Hydro is not considered renewable by ISO for whatever reason.
What does net imports mean?
Okay, so there are wires going between ISO New England, which is our independent system operator, and the New York independent system operator, the Canadian maritime provinces, and also some links to Hydro Quebec, for instance, and things like that. So if you have a net surplus of generation in one of these other places, the price may be low enough that it displaces, for instance, the need to burn more natural gas in New England or something like that. So that's why it's a net import. It can be an export under some circumstances. Typically, it's an import, not a large one. Usually, the usual ranking is natural gas, nuclear,
Sorry, everybody.
and hydro. If you go over to the left there quickly, you can see how these things vary with time. So that's the resource mix graph over the last.
Click on the 2 double left pointers for the key.
Yeah. So there are basically
Down.
switch the thing to renewables, and you'll see that what is otherwise very hard to see generally. That little thin line at the bottom splits up into a number of different renewables: wind, solar, burning trash, that's considered a renewable. Burning wood waste in New England is considered a renewable. And there's some methane gas comes out of landfills. And those are all considered renewables.
Click on renewables, Peter, underneath the word resources.
Yeah, right.
Underneath resources.
Yeah, yeah, right. On the top there. Yeah, there you go. So you see currently the color code is refuse is dominating over wood. Wind and solar are pretty low. And solar is coming up over the course of the last few hours because it's gotten clearer.
So it's around 6:30 or 7.
You have a question?
I have a question on another topic, please. Lithium.
Yeah, but excuse me a second. Whoever's speaking, Mike Alexander had his hand up and has been waiting. So just let him go
We've
first.
been
Then we
waiting
can
too,
go.
though. We had our hand up too first.
All right. So fight over it. Go ahead in the audience
Okay.
at the community center. Go ahead.
I'm trying to shift gears a little bit to another topic, which is related. Lithium-ion batteries, as I understand, have been around for a while and are some of the best storage devices. I'm wondering if any work is being done on other kinds of batteries that would be more efficient, such as polymer-based batteries. Do you know anything about better storage batteries?
Yeah, there's a lot of work on batteries. The basis of these batteries, lithium ion included and such, really dates to this electrochemistry revolution in the 19th century, and then a number of little blips in the 20th century, and then very recently it just took off. And it's taken off. It really got driven by Sony, which needed batteries for their video cameras and stuff like that needed a fair amount of juice available and had a reasonable ability to be reliable. And they sold these cameras not just for hobbyists but for professionals. And so lithium ion really relates to the use of lithium in a sense as a replacement for the zinc if you think of the alkaline battery. And then there are a whole bunch of different materials that are used for cathodes and for the electrolytes, and they change favor and flavor over time as people figure out better ways to manufacture and stuff like that. And so the real challenge on those kind of batteries is being pushed very hard by the consumer demand for cell phones and things like that, and for electric cars. For the grid, most of those things are not very useful. The lithium ion batteries can play a role in the very short term kind of basis of things, along with potentially with ultracapacitors. But for a long term solution to the Dunkelflaute problem, especially the kalte Dunkelflaute problem, you need very cheap batteries, and those are not going to ever be lithium batteries. And you don't need the main advantage of lithium, which is it's a very light material. So there are two companies came out of MIT. One that was started by people associated with the chemical engineering department that realized that we have a lot of expertise in doing big scale electrochemistry, which is what you need to do, right? In the industries that do electrochemistry, not as batteries, but as methods of producing materials, aluminum, for instance, and some other materials. And those are big electrochemical cells. So if you were to try to use that kind of technology, you could make a cell. Now, these cells generally operate at elevated temperatures to significant extent, so that's less of an issue, of course, with the battery for the grid, because you have a lot of volume, so walls are far away, and so that the heat losses are low. If you try to do it in the house, and they tried to build a unit that would be the size of your furnace, essentially, the heat losses are just tremendously high. The other one, which is more successful, I think, financially, is Form Energy. It's based in Somerville, and they are actually building batteries that go back to the old lead acid type of battery, but instead of lead, they use iron. So they rust the iron. That's the simplest chemistry of it in a sense. And iron is cheap, and we know how to rust it. There are some issues about the specifics for the electrolytes and things like that, but that gives you the ability to build very big batteries that are relatively cheap. And they are in the process, and that's what I was going to point out on some of these business stories. They have signed some contracts to actually put prototypes of these things in the field where people have a lot of wind energy, particularly such as in some of the open plains, Great Plains in Minnesota and stuff like that.
All of this discussion is about DC electricity, but what we receive is AC.
That's right.
And so a good part of what's going to be involved is going to be conversion to AC. I don't know that figured into anything that the numbers for efficiency that Ted was talking about. You can comment on that in a second. And distribution. In the 30s, distributing the electricity was a very, very big deal. I mean, this was something my father said was, when he was an electrical engineering student, was a major part of the research. And what we have really is just localized distribution systems. A few of them hook up together. Ted was talking about the New England system hooking up to New York. We don't have a national system at all. Texas has no connection to anybody else, which ran them into a lot of trouble. And so
let's keep politics out of it, okay?
Wasn't politics.
Well,
there
Texas,
was a tongue in my cheek, Mike. I didn't want to derail you.
Yeah, Texas wanted to be independent for various reasons from the two interconnects. I'll correct that statement that we don't have a national system. We have three parts to it. We have the northeastern and the eastern, southeastern, and the midwestern part, which forms an eastern interconnect. And then there is a western interconnect, and there's pretty much nothing in the middle in a sense. And so those two were independent, and Texas wanted to be independent for reasons that have to do with the Lone Star State. A long story about that, but the relevant point is there are little kind of connectors between all those. But yeah, the Northeast has been integrated for a long time. In fact, we had a perfect example of that in 1965 when we had the Great Northeast Power Blackout. A small relay in the Sir Adam Beck Power Station on the Niagara River in Canada near Toronto failed, and it blacked out everything all the way down to Washington, D.C., basically along the East Coast. We had another example of the blackout that happened in 2003 when a more complicated series of events happened in the Midwest that ended up blacking out everything but New England and from the Hudson River south or southwest, whatever. So you ended up with the Midwest blacking out. You had Canada, Eastern Canada blacking out. You had New York blacking out. There was a cut right at the junction between the ISO New England and New York, and there was a cut between the Penn Jersey connection to the New York, and both cases there were millions and millions of people who blacked out because they were all interconnected.
Yeah, well, the question that I was getting at was DC to AC conversion.
Yeah,
because the sources that you're talking about are DC.
That's right.
And
so
not all of them, but
conversion is used to be done by machines.
Let him finish.
Ted.
Yeah, no, so my question, you may want to I'll expand on the scope of that, is, the efficiency of that conversion.
It can be very high. The original conversion for AC to DC was by rotating machines. So you had a motor that was AC or DC, and you had a generator that was DC or AC, and they were connected by a mechanical shaft. And those operated, in the 85 to 90% efficiency, as do any electric motors or generators. The breakthrough was to replace motor generators with switched arc rectifiers, and that basically efficiency was about the same, but you got rid of all that heavy machinery, and now it's all solid state, basically high voltage semiconductors, and the efficiency is, again, it's in the 90% range. We have a perfect example of that, actually, if you go west of here towards where the Commonwealth Fusion is building the fusion reactor. Right near there in Ayer, there is a terminal for a DC line that comes from Canada, and it gets converted to AC at that point, and then the energy is distributed throughout New England, and potentially could go back the other way. It doesn't usually, but up to 2,000 megawatts can be brought down from Canada through that DC line, high voltage DC line.
I think we need to stop now because it's 15 minutes after, and I have to leave shortly.
Okay.
That
last video, which is an hour-long video, is an excellent one. It's produced by the Royal Institution in London, and you can actually see the presentation coming from the theater, renovated, but the theater that Michael Faraday gave his first lectures on electromagnetism about 190 years ago, in the 1830s.